Today we're going to continue in chapter 30. Now we're going to continue calculating the magnetic field from different wires, different shapes. So last time we calculated the magnetic field from an infinite straight wire, and we have found that the magnetic field from an infinite straight wire equal to mu 0 I over 2 pi r. If you look at that equation, mu 0 I over 2 pi r, mu 0 is the permeability of the medium. I is the current in the wire. R is the distance between the wire and the point that you're trying to find the magnetic field at. And if you look at that equation, you'll find that the magnetic field is actually constant at the same R. So if this is the wire, the magnetic field at that point, at that point R is the same at that point at that point. So at a circle around that wire, the magnetic field is constant. Okay, and the magnetic field here is, we can find this is the magnitude of the magnetic field, and the direction can be determined by the right hand rule. If this is the direction of the current, the magnetic field will actually, if this is the current, the magnetic field will be round. It will round around that wire, and this. So now we can calculate the magnitude and the direction of the magnetic field. Not only that, now we can design our own magnets. In chapter 29, we were talking about the magnetic field regardless of the source of the magnetic field, and we were assuming that the magnetic field comes from natural magnets, that we find them in nature. Now we can design our own magnet. That depends on the shape of the magnetic field that we want, and we'll see more of magnets from now on. One more thing to say: the unit for the magnetic field is Tesla. 1 Tesla is equal to 10 to the power 4 Gauss. The Earth field, the Earth is a big magnet. Actually, it is a magnet that has a magnetic field equal to 0.5 Gauss, half a Gauss. Now let's assume that we have two wires, not only one wires, two wires. Wire number 1 and wire number 2. The direction of the magnetic field, the direction of the current on those wires is in that direction. So it's actually towards you. Now we need to calculate. We need to know if will this wire have an effect on that wire? Are we going to feel forces between them? Let's find out. If there is a wire, if there is a current in that wire, what's going to happen? It will produce around it a magnetic field. So what will be the magnetic field at the location of that wire? Magnitude and direction. The magnitude is mu 0 over 2 pi r. I'll go back. It's mu 0 over 2 pi r. This is the magnitude. So at that wire, the magnetic field from wire number 1 is mu 0 times that current, I1, divided by 2 pi times that distance, r. This is the magnitude of that wire. What is the direction? What is the direction of the magnetic field at that wire? What is the direction of the magnetic field from wire number 1, Ala, at wire number 2, Bishoy? What is the direction? Direction of the magnetic field. So this is the wire that carries the current in that direction. So this is the wire. So the magnetic field around it will be circles around it. So at that location, somewhere in here, it's going to be up. So the magnetic field at that wire is up. Now we need to find, now this wire has a current and is located inside a magnetic field. What does that mean? There will be a magnetic force on it, because we know if you have a wire inside a magnetic field, there will be a magnetic force on it. What will be the direction of that magnetic force? Well, this is the direction of the magnetic field, that's up. This is the direction of the current. So that means that the force on that wire is going to be in that direction. So the wire, this wire will be attracted to wire number 1. It will be attracted to wire number 1. What's going to happen to wire number 2? Why? Why will it be attracted to wire number? What's going to happen to wire number 1? Amr is saying it will be attracted to wire number 2, and I'm asking him why. Because the same thing again, the same thing is going to happen again. which is this wire, wire number 2, will produce in here a magnetic field. What will be the direction of that magnetic field? Down, because here it's going to be down. So now at that wire, the magnetic field is down. So this is the magnetic field, and this is the direction of the current in that wire, So the force is going to be into that direction, applying the right-hand rule again. So what's going to happen to those two wires? They will be attracted to each other. Okay? Now we have calculated the direction of the force on each wire. We have calculated the direction of the force on each wire. So if the two wires carry the current in the same direction, they will be attracted to each other. This is one thing that we have got from that problem so far. Now, this is the direction of the force. Can we calculate, let me finish, can we calculate the magnitude of that force as well? Any idea?
It's 1 times A2, right?
You try to memorize something from high school.
No.
Okay.
It's by understanding electricity, I want to apply it in...
Okay. So what's going to happen then? Those two wires?
The two forces of each wire
Mm-hmm.
will, force number 1 will act on force number 2, right?
No.
Be equal to force number 2.
What if you have, let's go back one step. Chapter 29. Let's go back one step, chapter 29. If you have a wire, carries a current, and you put it in a magnetic field, there will be a force on it. What is the magnitude of that force? IL cross B. And if L and B are perpendicular to each other, which is that case, then it's going to be simply ILB. Which means that this wire will be affected by a force equal to the current in it, I2, times its length, L, times the magnetic field, P1. The magnetic field from wire number 1, which is mu0 I1 divided by 2 by R. So if you multiply the magnetic field by I, this is I1. This is the magnetic field from wire number 1. If you multiply that by the current in wire number 2, you add here I2. And if you multiply by the length of that wire, you multiply by L. So it's going to be mu0 I1 I2 divided by 2 by R. This is the force acting on that wire. I said L. Yeah, times L, of course. So what will be the force acting on that wire? Why is it the same? That's one way to look at it. It's the same thing. If you do the same thing again, you get exactly the same equation. What? They have, no, actually, they do not have the same current. One of them has an I1, the other one has an I2. True. So it's going to be the same force again. This is one answer to look at it. If you do the calculation again on on wire number 1, you get the same formula. This is one way to look at it. Can anyone give me another answer? Yeah, Newton's third law. Forces happen in pairs. So, and those two pairs of forces, if they are opposite in magnitude, they will be also equal. So they are opposite in direction and they will be equal in magnitude. That's Newton's third law. So by Newton's third law, you can just say that actually the force on that wire, it's going to be the same force on that wire, but opposite in direction. Now, excuse me, forces? Each one of them acting on the other one. So each one of them has a force, only one force acting on it, and exerting force on the other one. And if you remember when we talked about in Physics 111 about Newton's second law, we were mainly concerned about the forces acting on the object, not from the object. You remember that? This is our concern should be only on the forces acting on the object, not the forces from the object. Okay. So now we can calculate the forces between two wires carries currents, and if those currents in the same direction. Sorry, I'm going to actually take your question in a minute. Now let's assume that they are in opposite direction. So two wires, two wires, instead of having the same direction of the current, one of them is in the opposite direction. What's going to happen? They will repel each other. If you do that same thing again that we have done now for the two wires that carry the currents in the same direction, you'll find out that the forces between them will make them repel each other, but it's the same formula for the magnitude again. The magnitude of the force is going to be mu0, I1, I2 divided by 2 by R, and this will be the force per unit length. I'll say it again. The force in that case is going to be mu0, I1, I2 divided by 2 by R, and this is the force per unit length. Or you multiply it by the length, you get the force acting on that wire. So if you have two wires, and if those two wires, one of them carries a current IA, and the other one carries a current IB, there will be forces between them. Those forces can be easily calculated if we know the magnetic field produced from IA at the location of IB, then we can find that force F. And if you do this, that's what we get. We get the force acting on wire B equal to mu0 IA IB times the length of the wire divided by 2 by D, where D is the distance between the two wires. And this is the same force if acting on wire A. Actually, I'm assuming that they are infinite length, because actually otherwise that formula is not going to be the magnetic field from a finite wire. This is the magnetic field from infinite wire, and that takes us back to what is the definition of infinite. Simply, the length of the wire is much, much longer than the distance between the two wires. So it can be 1 meter wire, which is not really infinite, and the distance between the two wires is few millimeters. Then we can consider that wire to be an infinite wire. The length of the wire is much longer than the distance between the two wires. Okay, this is a very simple quiz. Two wires have currents in the opposite direction. What will happen to the wires? They will repel. Two wires having the same current in the same direction, they will attract. So let's not waste time. And here, okay, this is a little bit harder quiz. Now we have a wire carries a current I. This is the straight wire, infinite straight wire, carries a current I, and there is a loop beside that wire that has also a current I. And we need to find the force X, the net force along the X-axis on the loop. Is that going to be positive, negative, or is it going to be 0? The net force along the X-axis on the loop. On the loop. Why 0? Why 0? Okay, Omar, why 0?
The left side of the loop is going, the top side is going in one direction and the bottom side is going in the other direction.
But those are along the y-axis. So actually, I'm not really concerned about the forces, the top force and the bottom force. I'm talking about the forces along the x-axis. The question is asking mainly about the forces along the x-axis, not the y-axis. So I should not really pay attention to F top and F bottom. No, actually, on that wire, on that segment of the loop, the force is to the left. And that segment of the loop, the force is to the right. So why 0? That's good. The direction of the two forces are opposite to each other. But are they equal in magnitude? Yeah. Which one will be more? F, the force to the left or the force to the right? The F force to the right. Because actually, if you look at the formula again, R is at the bottom, so means you increase R, the forces get decreased. So there's an inverse proportion between the distance and the force. Lena? Okay, again, let's go back. This is the formula for the forces acting between two wires. It's I1, IB divided by L divided by 2 pi, the distance between the two wires. So if you increase the distance, what happens to the force? Decreases. You increase the distance, the force decreases. Now, let me finish. Now, the force here, that wire here is closer to that wire. So it will be affected by a force equal to mu0 I times the length of that wire divided by 2 by that distance. While that wire, that segment of the loop the force on it will equal to mu0 times I divided by 2 by that distance. Obviously, the two distances are different. The one that has a shorter distance, the segment that has a shorter distance from the wire, from the main wire, will have more force, which means that the force to the left is more than the force to the right. That's why the net force along the x-axis is going to be negative. And negative means direction. Abdullah? Hussein? Who wanted to ask something? Hussein? Okay. Okay. That wire. What is the direction of the magnetic field at that location? It's into the screen. So now you have on that. It bends. It's a circle. So if you draw a circle around that wire, at the location of that segment, the circle is going to enter the screen. Okay? So this is the direction of the magnetic field. This is the direction of the current in that segment. This is the direction of the force. So the force is to the left. Okay? Well, I'm not asking you about the force on the wire, on that wire. Oh, you tell me. What is those are two wires. This and this are two wires carries currents in the same direction. The forces will be in them is going to be an attractive force. What? Okay. Okay. That was what we have been discussing for the last 15 minutes. Let me say it again. Two wires carries current in the same direction. This will produce a magnetic field in here, and this will produce a magnetic field in here. Let's take one by one. What will be the direction of the magnetic field produced by that wire in that location? This is the direction of the current. It's going to be up. So this is the direction of the magnetic field. This is the direction of the current. What will be the direction of the force? Left. To my right. Now, this will produce a magnetic field in here. In what direction? Down. So this is the direction of the magnetic field at that wire, and the current is in that direction, right? What will be the direction of the force? So that means that if we have two wires carries currents in the same direction, there will be an attractive force between them. And if they are in the opposite direction, there will be a repulsive force between them. Okay? So, going back to the left segment of the loop, what will be the direction of the force on that segment? Alaa. On that segment, what will be the direction of the force? Why right? Yes, because you can read. Other than that. Because that wire, that infinite wire, produces in here magnetic field that's into the screen. The magnetic field is going to be into the screen again. This is the direction of the magnetic field, but what will be the direction of the current on that segment, on the small segment? Down. So what will be the direction of the force? Outward. That's why it's to the right. Okay, guys? So that's the problem. No, this is... Why should I put it? Yeah, because I'm actually explaining to you what happens. It's up to me. But I believe, Amr, but I believe you can do it. Yes. Excuse me? Yeah, of course. Of course I have to give you the direction of the current. Otherwise, yeah. Abdullah?
دكتور هو التوب اند بوتtom موف عشان هما عشان they act on each other مش عشان الواير اللي جنبهم دي.
Can you listen to this? The top and bottom what?
They actually move like the force.
No, actually they will not move. If you look at the top and the bottom part, each small segment of it will have its own force, top and bottom, but they will actually be equal magnitude and opposite direction. So if we, I'm sorry I forgot to get the markers, but if I draw the forces on the top segment, the force at the segment at the part to the left is going to be strong, and it's going to decrease as you go to the right. Concentrate, guys, on what I'm saying. May I use this and a piece of paper? No, I'm going to take the whole thing. Okay. This is the top segment, right? That's the top segment. I'm going to draw the forces in it. The force here is going to be, this is the force at that part only, this is the force. And the force here is going to be less, the force here is going to be much less. And the reason is, you go further away from the wire, the magnetic field decreases. And as if the magnetic field decreases, the force decreases. Right? So the forces here is not going to be equal. And that segment is going to be different than that segment, different than that segment, different than that segment, and so on. But at the bottom part, this part will have the same force, opposite direction. Those will cancel out. In here, this force and that force will be equal in magnitude, opposite direction. They will cancel out. So the top part and the bottom part, they will give you zero force. So if I ask you guys in here, what will be the force along the y direction? It's zero. If I ask you about the magnitude of the force on that segment, this is really hard. That's not easy. Yes.
اللي حضرتك بتتكلم عنه ده مش هو في that direction. ملوش دعوه
No.
بالواي direction لان the eye is parallel to the y direction هيبقى عليه force خالص in the y direction. هيبقى نازل كده. هو بينزل تحت. force ايوه بس force تبقى فوق. ده magnetic field sorry.
Did you know what was the confusion here, guys? Did you notice? He was actually talking about the magnetic field and looking at the force. He was talking about the direction of the magnetic field and actually considering that this is the same direction of the force. On the top part, everywhere to the right of that wire, the magnetic field is into the screen. And this is the direction of the current, right? So the force is going to be up. But it's going to be different from segment to another, as I explained on that paper. Now I'm going to bend that wire into a circle. And I need to find out what will be the magnetic field in the center. In the center. I'm talking about the magnetic field, not the force. Into the page. That's the direction. That's the direction. Why 0? Yeah, it's symmetric. But how come? How it will cancel? How it will cancel? How come?
الهدف يا جماعه الهدف كله into the page. صح.
So how come it will cancel out? Shady. Bishoy. It will not cancel out. So the answer is not A. So we have to actually use Poisson-Vallot to find out the magnetic field, and that was, if you remember, I'm going to go back. If you remember, that was that. That was that. The magnetic field from a segment carries a current P, carries a current I equal to mu 0 I over 4 pi times dl, the length of that segment, cross r divided by r cubed. So I'm going to do this. Does anyone have a marker, guys? I'll manage. There is? But is there a marker? So let's do this. Let's try to do it. No, that's okay. Let's do it. We're going to apply that on the circle. Let's identify each term carefully. What's mu 0? Constant. If I need to find the magnetic field from the whole circle, I have to integrate from the beginning of the circle to the end of the circle. Okay? So I'm going to do that integration. The total magnetic field is the integration of that right-hand side. I'm going to do that integration. Mu 0 is constant, goes out of the integration. The current is constant, does not change from a point to another, it goes out of the integration. 4 pi is also constant, let me finish. 4 pi is also constant, that also goes out of the integration. dx, that is the small part of the wire, small part of that circular wire, I'm going to call the length as dl, not dx. Small part in here that has a length of dl. Small part. Anywhere. Cross r. What's r in that case? The distance between that segment and the point that we're trying to find the magnetic field at, which is r capital, divided by r cubed. R capital, that r capital and that r cubed, those are constant. It doesn't matter where you take that segment, the distance between the segment and the center is always constant. Yeah, of course, yes. And Abdullah is saying, sorry, Omar is saying, guys, can you write the formula, put it in front of you, because I want you to look at it. I write that formula again. On your paper, in a piece of paper, write it and put it in front of you, this formula. Instead of dx, write it dl. I know, just wait. Guys, write it down. And instead of dx, put dl. dl. Okay, you ready? Okay. Let's go back to the diagram then. Now, DL and R are always perpendicular to each other. DL is the tangent to that segment, and R is the radius. Tangent and radius are always perpendicular to each other. That's why the cross product will give you 1. So it's going to be DL times R divided by R cubed. DL times R divided by R cubed. And R and R cubed, those are constant. This is the R, capital R. That's the dead distance, which is the distance between the segment and the radius, and the center, which is the radius. So you end up having mu 0 I divided by 4 pi times divided by R squared times the integration over DL. What is the integration over the length of that wire? It's the length of it's 2 by R. It's 2 by R. So, and if we do this, you find that the magnetic field actually in the center equal to mu 0 I over 4 pi R squared times the integration over DL, which is 2 by R. You get mu 0 I over 2R. That's like, as Bishoy said, that it's not going to be 0 because he actually used the right hand rule and looked at the direction of the magnetic field at the center, and he found out that the direction will never cancel. Each component, each segment will have a direction in the center, and the direction is going to be into the page in that case, into the page. Okay, guys, it's more interesting actually. What I did now, we took a wire, infinite wire, and we calculated the magnetic field from an infinite wire. Then we took a wire and we bent that wire in a form of a circle, and we found the magnetic field in the center of that wire, of that loop. Actually, he got choked on the loop. I have too strong magnetic field. Now, instead of calculating the magnetic field in the center of that loop, I want to calculate it somewhere at the axis of that loop, here, there, or there, and that's the problem. So it's not exactly at the center. I'm going to calculate it out of the center, somewhere at that axis, on the z direction. So I have a loop. This is the yellow line. Current goes from the top and goes into the bottom. So this is the loop. It comes like this. It's a circle. It's a circle. And I want to calculate the magnetic field in here. It's a circle. Like this. Excuse me. Hussein, this is the loop. I put it that way. If you look at my hand, so now the current is coming out from here in here. Okay? And I need to calculate the magnetic field somewhere in here. From the top coming out, and then the bottom it's going into the page. Okay? Now we need to find the magnetic field at that point somewhere in here. So what I'm going to do, I'm going to take a segment on the top, and we'll try to find the magnetic field from that segment at the point that we're trying to find the magnetic field at. I will take a small segment at the top. At that small segment, what will be the direction of the magnetic field in here? It's DL cross R. It's perpendicular to DL and perpendicular to R. So this is going to be the magnetic field. This is going to be the direction of the magnetic field. Perpendicular to R and perpendicular to DL. I'll tell you why.
How is it perpendicular to the length? How
Okay? That's for the segment on the top. How about the segment at the bottom? I'm going to choose a small segment at the bottom. It's going to be somewhere in here. And if the two segments carry the same current, which is that the case, and if they have the same length, and I'm going to choose them the same length, that means that you have two components of the magnetic field, one along that direction and one along that direction, which means the y component will cancel out, and the only component that will survive is the component along the z direction. So now the magnetic field from that segment, from that loop, at that point, is going to be pointing out. It's the same thing. This is what I said on day one. You build on each lecture. It's going to be point out. It's going to be pointing out. So this is the direction of the magnetic field. So actually we'll be interested only in the component, in the z component of the magnetic field. So that magnetic field dB, I will only concentrate on the z component because this is the surviving component. And the other component will die, it will cancel out, so that I'm not going to consider it. That magnetic field, that component dB is going to equal to mu 0 I divided by 4 pi times dl over r squared. So mu 0 I over 4 pi times dl over r squared. Look at this. What's r? R is equal to r squared plus z squared. So it's dl over z squared plus r squared. Then, excuse me? Why didn't I write what? Because dl and r are perpendicular to each other. So dl, it's dl times r over r cube. R will cancel with the cube. You get only r squared. It's the length of that segment. You choose a segment in here. This is the loop. This is the loop. You choose a small segment that has a length dl. Yeah, and then you do the integration from the beginning to the end. And no, it's not the same. We'll wait. Mahmoud, what? Tariq. Okay, I can explain that to you after class. It's very easy. Oh, because you have a segment. This is the loop. Okay, this is the loop, and you try to find the magnetic field in here. Does anyone have a CD? A CD? No, sure. I can give you another one if I should ruin it. Yeah, CD is actually look. Okay, so now this is the loop, and I'm trying to find the magnetic field in here. So I'm going to choose a segment in here, small segment, that has a length dl, and carries a current I, and I'll try to find the magnetic field at that point. That distance is the distance that I call it small r. That distance is that length. This is, I call it z. And this, I call it r. Okay? Okay? Okay, this is the direction, this is the current, and this is R. So R and current, the magnetic field has to be perpendicular to both of I and that R. And that I and R, they are in that plane. So that means that the magnetic field has to be perpendicular to that plane. Oh, you apply the right-hand rule then. You apply the right-hand rule then. That's a very good question here. Assume that segment on the top, that's current that's coming out. That's coming out. Now, draw a circle around that dot on the top. Draw a circle around it. Here. And if you draw a circle, this is the circle. Right? Right? And it's coming out. So you draw it, the magnetic field is going to be tangent to that circle at that point. So if you can just draw a circle around that dot on the top, you'll find that this is the direction of the magnetic field. And if you do the same, let me finish. And if you do the same at the cross, if you draw a circle centered at that cross and put the direction of the current to be into the screen, you'll find that this will be the direction of the magnetic field, down. Excuse me? Yes. It does, but at that point, you need to find the direction of the magnetic field at that point. So what you do is you draw the tangent to the circle at that point. And if you do that, you'll find this. Bishoy, would you like to come and explain? Then. No, actually assume that dot on the top, it's a wire, it's an infinite wire that has a current that's coming out of the screen. Okay? Now, assume that this is your center and draw a circle around it. That circle has to touch that point. Draw a circle centered in here, and touching that point. If you draw that circle, this is the circle. And this will be the direction of the magnetic field. At that point, if you draw the tangent to the circle, this will be the direction of the magnetic field at that point. And if you do the same thing again for that cross, assume that that's a wire that's going into the page, into the screen, and draw a circle centered at that cross. Then at that point, draw the tangent to that circle, you'll find this is the direction of the magnetic field. Okay? Okay? Okay, guys? Sharif. May I use that? Sorry. Okay. Now, you have a wire coming out of that page. And this will be the magnetic field around it. What will be, coming out, so this will be the direction of the magnetic field. Correct? At that point, what is the direction of the magnetic field? At that point, what will be the direction of the magnetic field? It's the tangent at that point. At that point, what is the direction of the magnetic field? And that's what I did. I centered myself around the top, draw a circle, and found what will be the direction of the magnetic field at that point, and that's the pinkish color arrow. And I did the same again at the cross, and I got that bluish dB. Okay, guys? Because in here, it's somewhere in here. Omar, it's going somewhere in here. It's going to be like this. Okay, so it's going to be like that. Okay? Just draw it. Print that page out, draw a circle, and look at the direction. It's somewhere like that. It's somewhere. Okay, Omar? Okay. The current at the point X, what is the direction of the current? X. What does X mean? Into the screen. The current in here at that point is into the screen. This is the current. Then draw a circle. Then there's the X, okay? Then you draw a circle around it. And in here, what will be the direction? This is X. This will be the direction of the magnetic field at that point. This will be the direction of the magnetic field at that point. Into the page. So this will be the direction of the magnetic field. Circles around it clockwise. No, oh no. Oh, actually, Z? No, 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 no. Into the page. No, I don't know. I don't want to use the Z axis because I don't want to confuse them. There will be no magnetic field into the screen, into the page. No.
I don't understand how we apply it to
Oh, okay, that's something else. Okay, so I said now we know that the magnetic field from that segment, the magnetic field from that segment is from that segment of the wire, it's dB and it's in that direction. And that magnetic field, according to Boas-Savart law, it's mu 0 I over 4 pi times dl cross r, and dl cross r in that case is going to give you just r hat, which is unit vector. It's going to give you just dl, because they are perpendicular to each other, divide that by r squared. This is just the application. Now look at that triangle, r, z, and r, small r. In that triangle, I'm going to replace r by its value, which is r squared plus z squared. So replace it by r squared plus z squared. Okay? Then we agreed that I'm gonna concentrate only on the magnetic field along the z-axis, because the other ones, the one to the top, the component to the top and the component to the bottom, they will cancel with each other, equal in magnitude, opposite in direction. That's why I'm going to multiply that by cosine theta, because by symmetry the magnetic field is going to be along the z direction. So I'm going to multiply that by cosine theta, because this is the only component that will survive. Now, look, cosine theta, cosine that angle theta, equals to r divided by r. R capital divided by r small, which is r divided by the square root of r squared plus z squared. This is cosine theta. Now, plug in the values for cosine theta in here, that's what you get. Look at that equation. Look at that equation. In order to find the magnetic field, I have to integrate that equation from the beginning of the wire to the end of the wire, which is a loop, circular loop. I don't care about the segment. We need to find the magnetic field from the loop. So now look at this. Mu 0 is constant, goes out of the integration. I is constant, it goes out of the integration. Same goes for the 4 pi. R. Will R change? Again, remember what was R? That was R. If you take the segment here, here, or here, will that R change? So R capital is so constant, goes out of the integration. How about Z? If you take the segment here, there, or here, will Z change? No, Z goes out of the integration. So everything goes out of the integration, but dl, the integration of our dl, which is 2 by r. So I'm going to put 2 by r in here and look at the equation. So put the integration of 2 by r, that's what you get. Integration of dl, that's 2 by r, put it in here, that's what you get. This is an ugly equation that cannot be memorized, but the proof is not that hard. It's lengthy, it's long, but it's not that hard actually. But before actually we leave that equation, I want you guys to look at it. Assume that I'm trying to find the magnetic field at the center. This is the loop. I'm not trying to find it here, I'm trying to find it at the center, which means z equal to, put in that equation z equal to 0. Put in that equation z equal to 0. Then you get mu 0 I times r squared divided by 2 r to the power 3. And this will give you mu 0 I over 2 r. That was the previous example that I have given to you. Remember this. That's mu 0 I over 2r. That's where Bishoy said it's not going to be 0. Let's assume that Z is much longer than R. So that circle is here, and I'm trying to find, this is the loop that has a small r, 5 centimeter, and I'm trying to find the magnetic field at the end of the room, 10 meters away. So obviously, R can be ignored in here. So if you ignore R, that's what you get. It's mu 0 over 2 by I. It's mu 0 times I divided by R squared divided by 2Z cubed. One will say, how come you ignored R? You should ignore R in here. No, I didn't say that. We ignored R when we compared it to Z, which means that Z squared plus R squared, it's almost equal to Z squared. But I cannot ignore it in here. I said here that term can be simplified to only Z squared. Actually, Z, yeah. Okay, and that's what you get. So I'm going to call this. Remember, we had a quantity in chapter 29 that we called it magnetic dipole moment. And that was the current times the area. And in that case, it's going to be the current times by R squared. So if you multiply here by and divide by, you can call that I times by R squared the magnetic dipole moment. And that's what I did in that equation. That's the magnetic dipole moment. All what I did, I multiplied by pi, and divided by pi, and got that magnetic dipole moment. Okay, guys? That's the permeability of the medium. It's like epsilon 0 in electricity. Yeah, it's constant. Okay, guys. This is. I want you to read the rest of that part 1 before you leave, and I want you to read today and look at the e-lecture, which is part 2 of chapter 30. Part 2 of chapter 30. Look at it today.